Yeah. Okay, so I'm a big fan of analogies if you haven't figured out by now. So I want to present one to start class. Stoichiometry, in terms of like chemistry, is kind of like cooking or baking. You have a recipe, and you're trying to produce something. And so let's say that I want you to make a sandwich. Okay. What is the recipe for a sandwich?
Marlene Duncan, can you please come to the office?
It was based on like the information I have here. How much bread do you need? Oh no, but how much do you need to make a sandwich though? Okay, so if I were to make a recipe, what kind of sandwich do you make? So if I were to ask you for the recipe, it would be like 2B for bread. Okay. And then how many slices of salami should you put on a sandwich?
7.
I don't know, 2? 3. Okay, we'll go 3 pieces of salami. And then how much mustard do you need? Like one dip and spread? Why don't we just call it 1 mustard? Well, I don't mean, okay, so 1 like scoop of mustard. Okay. And what that makes you is 1 sandwich. How do you spell sandwich? Sandwich?
No. W-H-I-T-H.
Can't even spell. Sandwich. Okay. Does that make sense? That's your recipe for making a sandwich? Okay. Well, from a practical point of view, sometimes you have to consider what you have on hand. So here's my crazy scenario. Let's say that you go to your pantry and you discover you have 6 loaves of bread. So obviously you're not going to make a sandwich with all 6 loaves of bread, although you could try, I guess. You have a whole thing of mustard, but you only have 3 pieces of salami. How many sandwiches can you make? 1. Because you're going to be limited, key word today, you're going to be limited by the fact that you only have 3 pieces of salami. Does that make sense? That's what's going to slow you down. Let's say you had more salami. Could you make more sandwiches? Mm-hmm. Sure, right? Now, so let's say that you had a whole jar of mustard, and let's say that you had, I don't know, like 18 packages of salami. Maybe you could actually run out based on the fact that bread is what limits you. But from a practical point of view in chemistry, there is always something that limits you, and then the opposite of something that limits you is something that there's going to be excess of, there's going to be extras. Okay. In this example here, you're going to have at least 1, 2, 3, 4, 5, and most of that loaf of bread, that will all be extra. Does that make sense? And when you're done, you'll also have extra mustard left over, obviously. So my goal today is to add a new twist to our questions. They're not going to be harder, but we just have to consider the practicality of what is going to run out first. So let me do some examples. Actually, before I get to examples, I guess I have more pictures. Here's just a slide I found on the internet. I thought this was worthwhile. Let's say that you needed to make some cars. I don't know. The recipe for cars is that you need 1 frame plus 4 tires makes 1 car. Does that make sense? And so in this scenario here, you have 8 frames, you have 48 tires. Well, if you put 4 tires on 1 car, 4 on the next, 4 on the next, 4 on the next, 4, 4, 4, and 4, that fills up my 8 cars. Does it make sense to everybody that you're going to have tires left over?
Yeah.
So the limiting thing is your cars, your frame cars, and your excess is your tires. So, from a molecular point of view, here's kind of a similar concept. Let's say you have hydrogen and oxygen and you're making water. And you do it properly using the right ratio. Because I didn't balance that properly. The recipe says 2 hydrogens to 1 oxygen makes a water. And here's what you start with. So here, these guys right here, they can make some water. And these guys right here, they could make some water. And these guys right here, they could make some water. And that one can make some water. And that one can make some water. What did we run out of first? Okay, well, which one's extra? Okay, which one is which? These red ones right here, what are those supposed to represent? These guys are the oxygens. Those guys are the hydrogens. Sorry if that wasn't clear. It says you have 10 hydrogens and 7 oxygens, so the little white ones are the hydrogens and the big red ones are the oxygens. So based on that, which one did you run out of first? You ran out of hydrogen first. Which one do you have extras of? Oxygen. Okay, but here's maybe the key point here. You have more hydrogen than oxygen. See how there's 10 hydrogens to start with and 7 oxygens to start with? Why are there extra oxygens left over at the end of the day? Well, because the recipe doesn't call for 1 to 1. You need 2 of these for every one of those. Does that make sense? So let's just try 2 scenarios here. If you have 10 hydrogens, you would need 5 oxygens. Do you have 5 oxygens? Yeah, you actually have 7 oxygens, so therefore there's 2 left over. Approach it from the other direction. If you have 7 oxygens, if you wanted to use all of your oxygen, how much would you need for hydrogen? Well, 7 would need to double to give 14. Do you have 14 hydrogen? No, so therefore, like based on that logic, hopefully you can figure out that the hydrogen is what you have less of. But I want to use my fingers here, less of. You actually have more hydrogen than you have oxygen. But based on the recipe, you don't, even though you have more of one than the other, you still don't have enough to fill the recipe out. Does that make sense? Okay. Okay, let's try some questions then. It's very simple how we do this. You solve the question stoichiometrically, you do it twice. And whichever one gives you the lower number, that's the correct answer. Let me use my mustard salami sandwich thing. Based on the picture I have here, how many sandwiches can you make based on the bread? And I would say you can probably make like, I don't know, 30, 40 sandwiches based on bread. How many sandwiches can you make based on mustard? I don't know, 100 probably. How many sandwiches can you make based on the salami that's here? 1. Whichever is the lowest number, that's the one that limits you, and you have to go with the lowest amount you can make. So I'll often say this in stoichiometry. The work we're going to do is not harder. We're going to do the same work we did before when we read out a line of stoichiometry work, but we're going to do it twice. And whichever one gives you a lower number, the lower number is the correct answer because you can only make the lesser of the 2. Let's try an example. You have some copper and you have some sulfur. And we're going to try to make some copper 1 sulfide. You're going to notice these questions are a little bit different than the ones we've done before because I'm going to give you 2 numbers to start with. I'm going to give you a starting amount of copper and of sulfur. That's how you'll tell that these ones are a bit different because you get double the numbers. It just means you have to do double the work, that's all. So here's what I'd suggest we do. Let's start with copper, 10.6 grams of copper. We've been doing this for the last couple of weeks. What's the first thing you do when you get a grams number? We don't want grams, right? We want, okay, so we need a molar mass. What's copper's molar mass? Good job, yeah, 63.55 per mole. Then we need a recipe. So what are we trying to produce? It's this copper sulfur mix. And the recipe says 1 for 2. And then one more step. How do we finish this? Yeah, grams over moles. And we just need to find the molar mass of copper with sulfur. So, someone help me out here. Copper will be 63.55 times 2. Sulfur will be 32.07. Find me the molar mass of that last one.
159.
Thank you. Okay, does this make sense so far? Just basically, we're just doing stoichiometry like we've learned how to for the last little while. So, someone give me an answer for that if you could.
13.27.
Anybody else get that?
Yeah.
Cool. For sig digs, we only get 3 sig digs though, so can I call it 13.3 grams? Okay. I'm just going to write a sentence after this that I think you guys should write down for your notes, but we won't normally do this. This is how many grams of copper 2 sulfide you get if all of your copper reacts. But what if copper is not the thing that runs out first? Does that make sense? One of these 2 reactants we have too much of. It's kind of like the mustard and the bread and the salami. Something here there's extra of. So we've done all this work once. Now we're going to do all of this work a second time, only we're going to base it off of the sulfur number to start with. And then whichever number is lower, that's actually the right answer. I'm going to use another color now, just to differentiate it. Now do the exact same work based on sulfur. So start with 3.83 grams of sulfur. So the good news behind this is that like the work is very similar. You just need a molar mass of sulfur. So that's 3207. Is that right, by the way? And then you still go to copper sulfur. I think that's copper 1 sulfide. And sulfur's on the bottom, and it's a 1-to-1 ratio. And then, you know that 159.17 number? It's still the same number, so you don't have to calculate it a second time. So calculate all of those things together. Tell me how much copper 2 sulfide you could make based on the other starting value of sulfur. And 2.0 grams? Anybody else get that? Okay, I'm going to write this sentence here, but I don't need you to write this every time you do this, but I'm just going to say if all of the sulfur reacts. Okay, I have 2 different answers. Which one's right? The top one, yeah. Okay. Does that logic make sense? So just to reiterate, if you have, 10 loaves of bread and 3 slices of ham, with 10 loaves of bread, you can make 200 sandwiches. With 3 slices of ham, you can make 1 sandwich. Well, then it means you can make 1 sandwich because one of them runs out first. So if I were to ask you who the limiting reactant is, the limiting is copper, and the excess was sulfur. Copper is going to run out first, and there will be some extra sulfur left when you're done. How might you get rid of that extra sulfur? A filter? Or, you guys remember how we had a bunch of different separation techniques that were on a set of notes a few notes back? You can do things like filter it. You might need to do a distillation, a crystallization. But whenever a chemistry, a reaction takes place, almost always you have 2 reactants, and one of the reactants is completely used up. The other reactant, there's a little bit of leftovers, and you have to find a way to get rid of the leftovers. And so that's why you might need some separation techniques. Did that make sense? Okay. It's not harder. It's just more. Does that make sense? Like, you don't do harder work, you just have to do it twice. That's all. Let's try another one then. Let's say you take 10 grams of magnesium and 2.87 grams of hydrochloric acid. How much of each product will be produced? So again, you can tell that this is a different reaction in terms of having to do more work because I give you 2 numbers. Which one's going to be excess? Which one's going to be limiting? Can you tell just by looking at those numbers there? There's 10 grams of magnesium. That's a bigger number than 2.87 grams of hydrochloric acid. Does that mean that the hydrochloric acid is going to be the limiting one? I can't make that assumption because it really depends on molar masses. So we do have to kind of do this work twice still. Before I do anything though, I need an equation. So how do I get an equation started? It's a gas. What's it going to make? Well, MgCl goes together, but not like that though. It's MgCl2. that make sense? Magnesium is a +2, chlorine's a -1, so you need 2 of them. It's either solid or aqueous. Does anybody have a data sheet nearby? I'm gonna guess it's probably aqueous because I think chlorine is aqueous with most stuff, but I'm not sure. The state of matter probably doesn't actually matter all that much. It's not the end of the world. But anybody can look it up? It's aqueous? Okay. You need a 2 there to balance it. I think that's actually all you need for balancing. This one balances very nicely. Any issues with the start of this? Okay, the twist here is that now you have 2 reactants and you have 2 products. I think I taught almost all of you math. Sorry, I know you're not in my math class. Do you understand? Have you ever heard the word foiling before? Okay. Sorry, bear with me on this one here. It's almost like foiling in math. What we're going to need to do is figure out this magnesium, how much MgCl it can make. And then we're going to have to figure out this hydrochloric acid, how much MgCl it can make. But then we're also going to want to figure out this magnesium, how much hydrogen it can make, and this much hydrochloric acid, how much hydrogen it can make. You guys see how it's kind of similar to foiling, where like we almost have to make like everybody solve for everybody 4 different times? Again, the work is not harder, there's just more of it. So, you ever seen that before? Like the idea of like expanding? It's almost like in math you do x plus y and x plus y, you do like these ones times by each other. You don't need that for doing this. I just thought there was an analogy to what we do in chem or in math. So. Let's pick a number to start with. Let's do 10.1 grams of magnesium. What does magnesium have for molar mass? (2431). Okay, magnesium has to go to one of the 2 products, either the magnesium chloride or the hydrogen gas. It actually doesn't matter which one we go to, but we just got to pick one. So, someone pick one. Magnesium chloride. Sure, someone said something. We'll go to magnesium chloride. It doesn't matter, by the way. You could have gone to hydrogen gas because you're going to do that later anyways. So, the ratio is 1 to 1. Last step, we need magnesium chloride's molar mass. So I'll need some help. It's 3545 for chlorine. We'll need that twice. You need 2431. You need that once. Someone gets that one. 7531? 9521. And one more thing I need help with then. Can someone type all that in your calculator and find me what the grams is going to be when we're done? It's not harder work. There's just more. Anybody get an answer for this? 39.55. Cool. 39.55? Yeah. Okay, with sig digs I'll make it 35 points. 39 or 35? 39. So that'll be 39.6. Does that make sense? Okay, that's one. I'm going to recommend, I'm now going to do the 2.87 grams of hydrochloric acid, and I'm going to turn that into magnesium chloride. So, moles per grams, only now we need hydrochloric acid's molar mass, which will be 3646, I think. The good news is when you go to magnesium chloride a second time here, oh wait, we're not coming from magnesium, we're coming from HCl. You're still using 9521 grams per mole. And I think there was a 2 there. Am I going too fast, or do you guys, are you following this? All right, well, if someone does manage to finish this next line of work here, let me know what you get for an answer. What'd you get? 3.7. So 3.75? Anybody else get that? Yeah. Okay. Okay, so just a brief pause here then. Of the magnesium chloride, how much magnesium chloride will you actually make? The 3.75. This kind of sucks, but essentially all of that work you just did up here, useless. Because in theory, even though you have 6 loaves of bread and you could make 600 sandwiches, because you only have 3 pieces of ham, you can only make 1 sandwich. Right? So even though we just did all that work, half of your work is pointless. Does that make sense? So like this first work right here, this would have been based on the excess. Magnesium is obviously an excess, whereas hydrochloric acid is the one that's limited. So we've now done half the question because we figured out how much MgCl2 to expect. We also have to do some work where we calculate for hydrogen. So that'll look something like this. We'll have to take
Randy Bonnet, can you please call 100?
And go to hydrogen,
call 100.
and we'll have to go HCl and also go to hydrogen. We got 2 more lines of work to do. I've got a nice bonus here. It's not great, but I actually don't need to do both of these 2 now because I already know which one's limiting. See, if in the first half here, if magnesium was the one that's excess, and I know that hydrochloric is the one that's limiting, there's no point in me doing this magnesium to H2 one right here because I already know that's the one I'm going to cross off. So you don't actually have to do it 4 times. You only have to do it 3. I know it's not that much better, but does that make sense? In that, like, since I already knew that the magnesium to MgCl was the one I crossed off, by that same logic, the magnesium to hydrogen is the one I'm not going to care about either. So I just have to do 1 more line of work then. I need the 2.87 grams of hydrochloric acid. I need its molar mass. I need to turn it into hydrogen gas this time. And I need hydrogen's molar mass. Should put this up higher for you guys to see. Anybody else get that? And that would be of hydrogen. If you wanted to, I guess you could take the magnesium number and convert to hydrogen as well. But I don't see any point in doing that work because I guarantee you that number is going to be bigger than 0.795. Like it has to be, right? 0.0795. Oh, thank you. So, I mean, if you wanted to, I'll write this out here, but you don't probably need to. You could have started with the 10.7 grams of magnesium, and you could have done the magnesium molar mass of 2431, and you could have done H2 from magnesium, and you could do 2.02 grams per mole. But regardless of whatever number you get there, I guarantee you, like, why bother to do that work? It's going to be the one you cross off anyways. Does that make sense? So excess and limiting questions are not harder. There's just a lot more work to them. That's all. So to answer the final question then, the question asked us how much of each product will be produced. I now have that answer. You're going to make this much MgCl2, and you're going to make that much hydrogen gas. What's going to be extra? Magnesium. Yeah, you should also have some magnesium left when you're done. So it's almost like you take some magnesium and some hydrochloric acid, you react them together, And by the time you're done, you get some hydrogen gas, you get some magnesium chloride, but you still have extra magnesium left because not all of the magnesium actually reacted. And so from a technological point of view, you might need to find a way to remove that magnesium then and take it out of the reaction, because even though it's extra, you don't actually want it there anymore. You want to save it and use it again later. Does that make sense? Okay. One last question, I think. The last kind of question I can ask you for is to figure out how much excess reagent will remain. Okay. So, like in the last example we were just talking about there was going to be extra magnesium left over. Well, in this example here, of this aluminum or of this copper sulfate, one of these two things, there's going to be extra left over. So I'm not actually asking you how much product you're going to make. What I'm asking you is, how much leftover should you expect? Does that make sense? So let me walk you through how to do a question like this. Just like before, we need a balanced equation though. So you have some aluminum, you react it with copper 2 sulfate. What's it going to make? What was that? Okay, it will be Al with SO4, but we need to get the charges right now. What's aluminum's charge? What does aluminum have for a charge? What does sulfate have for a charge? Do they fit? Okay, so we have to make sure we balance these properly. If there's a 3 and a 2 here, you're going to put a 2 there. Bracket it with a 3. And you probably have copper left over. I don't know whether this is solid or aqueous. It probably doesn't matter in this example, so I'll just say solid, but you can look it up if it really made a difference. What else do I need to do before I even start doing any work? Good. Yeah, you gotta balance this thing. You're gonna need a 2 in front of the aluminum to balance it. You're gonna need a 3 in front of the sulfate, which means you need a 3 there. There's our balanced equation. You guys know how I give that analogy of foiling in the last example, where what you have to do is make aluminum turn into this one, and aluminum turn into this one. We also have to make this guy turn into that one, and this one turn into that one. All of that kind of true, but that's not what I'm asking you about. The question here does not really ask you how much product you're going to make, because all of that work that we did in the last example tells you how much of the products you're going to make. My question for you is, how much extra reactants are you going to have? Okay. So in order to solve a question like this, you don't always have to go from like one side of the equal sign to the far side of the equal sign. It is valid, if you want to take this one and turn it into this, or to take this one and turn it into that. You can still ratio things on the same side of the equation. So that's what we're going to do in this example here. You've got a 50-50 shot of guessing the right one first. Okay. So I'm just going to randomly pick one of my two numbers, and I'm going to change it from like aluminum to copper, or I'll pick the copper sulfate and turn it back to aluminum. I'm just going to pick one and hope that I get it right the first time. If not, I have to do it a second time. So like I'll start with the 10.3 grams of aluminum, for example. Like always, how do I get out of grams? Use a molar mass. 2698, I think. Is that right? Okay. But rather than take that aluminum and change it into one of the products here, change it into the reactant instead. Make it go to the 3 CuSO4 over the 2 aluminum. Turn it into the copper sulfate instead. And we just need copper sulfate's molar mass. So we need 6355. We need 3207. And we need 16 times 4 to find that copper sulfate molar mass. What'd you get? Thanks. Somebody else just want to confirm that before we move on. You got that too? Okay. So same thing. I mean, hopefully at this point, I don't need to be flippant, but like I hope you have the hang of doing stoic like this, because like that's kind of our unit. So just times it all together, I guess. Okay, I said earlier you got a 50-50 shot of getting it right. We guessed wrong. Okay, here's how I know. What we've just calculated here is that if you use all of your aluminum, you would need 91 grams of copper sulfate. Do you have 91 grams of copper sulfate? No. Does that make sense? So unfortunately, this work is no good because I had a choice of going aluminum to copper sulfate, and this is not logical because does that make sense? Like I don't have that much copper sulfate. So I gotta now do the other one. So unfortunately, this does not work because I don't have this much. You only have 51.7 grams. So rather than going from aluminum to copper sulfate, then what we actually need to do is do copper sulfate back to aluminum. So start with the 51.7 grams of copper sulfate and go back the other way. So in this case here, you're dividing by 159.62. It's going to be 2 aluminums for every 3 copper sulfates. And then you'll use 26.98 at the end. Sorry, that should be the 26.98. That's that molar mass of aluminum. One of the things you guys will notice when you do this is that this number here is just in the other spot. This number up here is in a different location. You're using all the same values. You're just changing the order up. Anybody get an answer? 5.825. Say that again. 5.823 then? Yeah. Okay. So now you calculated 5.83 grams of aluminum. Do you have 5.83 grams of aluminum? Yeah, you had like 9 grams or 10 grams or something. So do you guys get what I mean when I say you got a 50-50 shot of guessing right? You kind of just have to pick one of the reactants and solve for the other reactant. And if you get an answer that's too big, then you got it wrong. But if you have an answer that's too small, then you can work with this. How much extra will there be? You had 10.3 grams to start with. And you're going to take 5.83 grams that you're going to use. If you subtract them, that should tell you how much extra there is. So you just got to subtract those two numbers.
Or 3.7.
Does that make sense?
Yeah.
So I say this a lot. I've said it already like 5 times today. It's not harder work. There's just more of it. So I hope that I've structured my lessons in such a way that up to this point here, you feel pretty comfortable in doing like a line of stoic work where it's number, another number that you divide by, ratio, another number at the end. You just kind of cancel stuff out. If you're good at that, excess limiting questions aren't hard. Hopefully, right? It just means you need to take more time. So basically 2 possible questions. I could ask you to find the reactants, or I could give you 2 reactant numbers and ask you to solve for the products. This means you have to do it twice, maybe even 3 or 4 times, and you just pick whichever one's the lowest number. Does that make sense? Whereas if I give you 2 reactants and I ask you how much extra reactant there is, take one reactant, solve for the other. If that number is too big, then flip it around, take the first reactant, solve for the second instead, and just subtract the initial from how much you need to find out how much extra there would be. Does that make sense? Okay, one last thought. I know I don't have a question about it, but if you were to find all of these masses right here, this mass, this mass, this mass, and this mass, if you were to find them all, these 2 numbers and these 2 numbers should equal each other. Why? Why should your masses beforehand equal to masses afterwards? Good, law of conservation of mass. In theory, if you start with 100 grams, you should end with 100 grams. Does that make sense? One of the things that we'll discover in our labs, though, is that this number right here might be 100 grams you start with, and this one down here might be 99 grams. Sometimes you lose some mass. I'm using my fingers for quotes here. You don't actually lose mass, but sometimes you just can't capture it in a way that you can actually measure. And that's why we do things like percent yield to figure out how much was actually produced. Does that make sense? So, but if everything does work correctly, your starting mass and your finishing masses should add up to be the same as each other. Okay, any questions? Okay, so plan going forward then. Rest of today and tomorrow is some work time. Wednesday we're trying another quiz. To be honest, the only difference between tomorrow's quiz and the first one you wrote is we'll add a few things on those colorimetry charts that we learned about. So I might ask you some questions about flame tests and colors of solutions. And basically this sort of question. I won't throw a lot of these questions on because they take a lot of time to solve, but hopefully you'd agree. They're not harder. It just means that there's more work to do, that's all. So. Okay, take a 5-minute break, and then I guess you guys have about half a class to work on stuff. Finish your lab. You should be able to do almost all of your assignment now. You can't do every question, but you should be able to do most. I handed back your essay, by the way. I think you saw that. So good job.